Hello everybody. In this video I'm going to explain how to do a two-phase PSV calculation based on the homogeneous equilibrium method explained in the API 520 standard part 1 Annex C. I'm going to use Excel and Aspen HYSYS version 7.3. We need to calculate the required orifice area from this equation. A equals W divided by GM times KD times KB. W is mass flow rate, GM is mass flux, KD and KB are coefficient and correction factor defined in the API. The relieving capacity W is known, and to calculate the area we need to define the mass flux. To determine the mass flux through a nozzle of a PSV, the nozzle is assumed to be isentropic. Given the relief fluid composition, relieving pressure and relieving temperature, the inlet entropy can be calculated. From the energy balance for an isentropic process, we can show mass flux can be calculated as square root of -2 times VdP divided by V. You may check my other video for details of energy balance for an isentropic process. This integral can be readily evaluated numerically by direct summation over small pressure intervals. The midpoint integration rule is shown in this picture, which says integral of VdP is equal to delta P times V of P1 star plus V of P2 star, etc. P1 star, P2 star are the average specific volume values. We need to perform successive isentropic flashes starting from the PSV inlet conditions to generate fluid properties and numerically evaluate nozzle flow integral. 20 number of steps was arbitrarily chosen, which is 4.6% of the absolute set pressure for each interval. We need to generate a specific volumes or mass densities as a function of entropy, which is a constant value, and pressures. In this Excel sheet, column G, mass density is unknown. If we can get mass densities, we can calculate flux from the cumulative integral formula. The cumulative formula is I5, to keep it cumulative, minus 2000, 1000 is for the unit conversion, times E6 minus E5, which is delta P, times H5 plus H6 divided by 2. The last term is the average between the specific volumes. If we have a specific volume at P0 and a specific volume at P1, the average is VP1 star. We can use that average times delta P to get the integral. There are two methods to calculate, to generate the mass densities in HYSYS. The first one is using series of expander units, and in the design tab under parameters we define polytropic efficiency of 100. The number of expanders should be as many as the number of steps, which is 20 in this case. Second method is a shortcut and faster one by means of adding a property table. I'm going to explain in a couple of minutes how to add a property table. First, let me define the inlet and outlet stream to the PSV. Inlet stream is number 11 and is defined by entering the relieving temperature, the relieving pressure, and relieving capacity, which can be in terms of mole flow or volumetric flow, and also composition are known. If we check the conditions, this stream is liquid and molar entropy is 19.06. This entropy is constant through the isentropic flashes. This fluid flashes as it goes through the PSV, and the outlet stream 10 is a two-phase. All the other conditions and properties are automatically calculated. Now back to adding the property table. When we click on stream 11, if you go to the attachments tab, utilities, click on create and select property table, click on add utility. Mass density is a function of entropy and pressure. We need to define our independent variables. The first one is entropy, and we set the mode to state, and the second independent variable is pressure, and we set the mode to incremental. Now we enter the state value of 19.06 that we checked in the conditions tab. The lower bound for pressure is the relieving pressure, which is 250 psia, and upper bound is the destination pressure, which is 18.5 psia. Number of increments is 20. Now we have to define our dependent property. We click on dependent property, click on add, and select mass density from the list. Click OK. If we click on calculate and we go to the performance tab, we can see mass densities are calculated as function of pressures and constant entropy of 19.06. Now the only thing we need to do is to copy these data of pressure and mass densities and paste them into our Excel sheet. And same thing with mass densities. Once we enter these series of data, the specific volume and cumulative integral is calculated in our Excel sheet. And based on that, we can see the maximum mass flux. If the pressure value where the mass flux is maximized is greater than the total back pressure, the flow is critical or choked through the nozzle. In that case, we take that maximum mass flux to calculate the required orifice area. In this example, for the block outlet, the back pressure was 66.5 psia, and we see the pressure at the maximum flux is 99 psia. So this pressure is greater than the back pressure, which means this is a choked case, and we're going to use this mass flux to calculate the orifice area. Based on this mass flux, the orifice area calculated is 0.53 square inch, which means we can select the H orifice for this PSV, which has the area of 0.78 square inch. At the end, I just want to show that these two methods are the same. If you check the last stream from the successive expander units, stream number 33, the molar entropy, if we go to properties, the mass density is 0.6866. And if I go back to the performance tab, view, the mass density at the last step from this calculated property table is also 0.6860. So these two values are exactly the same and the two methods are equivalent. This includes my presentation.